whenever current passes through a circuit, a resistor, for example, what happens? We have seen that when we talk about the potential difference across a resistor, it is nothing but the work done in moving the charges through the resistor, work done per unit charge. Okay, so we have seen that W or V is equal to W by Q. Okay, so this V is the potential drop across the ends of the resistor, and Q is the charge flowing through the resistor, and W is the work done in doing so. Okay, so in that case, what I can write is W is equal to V into Q, right? So I know the charge as a product of current and time. So this I can rewrite this expression as C, V is equal to, instead of Q, I can write I into T. So whatever the work I am doing in passing the current through a resistor, what happens to it? It gets converted into heat. Okay, so amount of heat is generated and that heat is given out. So that is what we call it as heating effect of electricity or electric current. So whenever current passes through a conductor, depending on its value of the resistance, what happens is heat is generated. If the value of heat resistance is much larger, okay, so what I can do is, instead of writing expression in terms of potential drop, using the Ohm's law where V is equal to I into R, I is the current passing through the resistor, R is the resistance across the resistor, resistance of the resistor, and V is the potential drop across the resistor. I can substitute this I and R here so as to get I R into I into T, implies it is I square R T. So this work done, whatever we call here, that is generated as heat. So I can write it as H heat. H is the heat amount of heat energy which is given out when current is passing through a resistor is equal to I square R and T. So when I am given the value of I, when I am given the value of resistance over there, and it depends on time also. So if I allow current passing through a resistor for more amount of time, more amount of heat is generated. Okay, it also depends upon the value of the resistor. When we talk about the heating effect of electricity and its applications, we have so many applications wherein we use electricity to generate heat by passing it through a resistor. We can take the example of electric stoves, wherein we have a coil which will call it as a filament, and that filament will be having a high value of resistance. So you know that the value of resistance depends upon the length of the resistor. So instead of taking the normal straight wire, what they do is, in order to accommodate a large amount of length in a small area, they will take a coil. Okay, it's a coiled wire. So the coiled wire is a heating element over there. Either you can call it as a heating element or a filament. Okay, so its value is high. So when you connect it to the mains, wherein you have a potential drop of nearly 220 volt, okay, and some current is passing through it. So whenever current is passing through that heating element, heat is generated. Okay, that heat can be calculated, heat generated can be calculated through this expression. Depending on the situation, if I am given potential drop V and I am given the current through it and time taken, I can use VIT. Okay, if I am giving the resistance value, and I am given the current through the resistance, and I am given the time, then I can use this expression. From this expression, I can write that the heat produced in a coil or in a resistance is directly proportional to square of the current passing through it. It is directly proportional to the resistance of the resistor, and it is also directly proportional to time. So from this expression I can write this way, or else I can also combine these and then come to a conclusion, yes, this is the amount of heat generated. This particular expression is called Joule's law of heating, Joule. Joule's law. Okay, so we'll be able to find out if I is the current passing through a resistor, heat generated is square of the current. Okay, remember this point. If I take VIT, okay, if I increase the potential drop, the same expression I can write as VIT. If I increase the potential drop, that means V value is much higher. When V value is much higher, what happens is, for a given resistance over there, I value reduces. Okay, when I is very much less, that means I square is much less. Okay, when I square is much less, that means the heat generated is very less. Clear? This is the principle used in transmission of power from one place to the other place. The household supply, whatever you receive in India, it is 220 volt. Okay, you are getting it from a substation. Fine. And in the substation, you are receiving a voltage of nearly say 11,000 volt. Where is 220 and where is 11,000? Much higher, right? And in the transmission lines, if you see across the towers, from one tower to the other tower, it is of the order of 11,000 or much more. Okay, you have substations, and in substations you will reduce the voltage and then give the supply to the homes. By the time you get the delivery to the household connection, the power is reaching the household connection, the potential drop is reduced to 220 volt from a very much high range of say 11,000 or 22,000 volt. Okay, when the 22,000 volt potential drop is there, the current passing through it, that means whatever the value of resistance, the current passing through it must be very, very less. When it is very, very less, that means heat produced is also very, very less. Because heat is proportional to I square, what they do is they increase the value of V so that I is reduced. When I is reduced, heat produced when it is passing through the transmission lines is very less. So in order to avoid the heat loss to the surroundings, during the power transmission, they increase the value of potential drop and then thereby reducing the value of current to a very much drastical value. Okay. And one of the most important applications of this heating effect of electric current is fuse. Okay, you will be able to, you might have heard about this fuse wire. Very much commonly used. We may have fuse in the household supplies at different levels. We may have a fuse at a switchboard. We may have a fuse at a mains. Okay, we may have a fuse at individual partitions. Okay, so when we discuss about household electrical supply, there we'll be able to know what is the different levels and how it is distributed. Whatever the electricity you are getting to a household, how it is distributed across different rooms and across different boards. Okay, so the concept of fuse wire is that when current is passing through the fuse wire, okay, because H is proportional to I square, heat generated is more. When the current passing through the wire is more than what is to be passed, more than the maximum limit, when it exceeds the limit, what happens is the heat produced over there is much more to such a level that the heat generated will melt that wire. That is what we call fuse. Fusion is melting. The wire is molten and then the connection is cut off, thereby avoiding a high value of current to passing through the fuse wire to the appliance. So the appliance is safeguarded. Okay, so you may have fuse wires at the board level, switchboard level. You will also have fuse wires at the item level, whatever the household electrics items you are using, say an iron box. Okay, you may have a fuse wire. Or a computer, you are using a PC, personal computer, it will have a fuse wire. And UPS, uninterrupted power supply, it will have a fuse wire. So this fuse wire, the concept of the fuse wire is to safeguard the device when a high current is passing through the particular device. If the fuse wire is not having a proper rating, okay, So there will be a proper rating for the fuse wire. You cannot use any kind of wire as a fuse wire. Okay. What will happen is, if at all you are replacing and using a wrong wire instead of a prescribed wire for fuse, okay, then what happens is the fuse wire will not melt, thereby allowing the high value of current to passing through the appliance and thereby damaging the appliance. That is the reason fuse wire is of most important in the heating effect of electric current. Okay. Now, when we are discussing about the work done and the work done is converted into this particular thing, we will also be able to calculate what is the electric power. Okay. How do you calculate what is electric power? Power is nothing but work done by time taken. I can write this power as P is equal to work done by time taken. Whatever the work you are doing over here is nothing but V into Q. I can write it as this is equal to V into Q divided by T. I will be knowing that Q by T, I can combine this Q by T and write it as Q by T. If I club these two this way, that is nothing but rate of charge flow. This rate of charge flow is nothing but current. So same thing I can write it as V into I. So power P is equal to V into I. I can rewrite this as I into R. So I will get it as I square R. Instead of I, if I write using the Ohm's law, instead of I can write V by R. So if I replace this with V by R over here, what I will get is V by R whole square into R. So if I simplify this, it will be V square by R square. This is equal to, into R. This will be equal to V square by R. So I can use any of these expressions, this one, or this one, to find out what is the power used. Okay, what is the power used? To find out the power used, power rating of a device. Whenever you buy an electric device, say an immersion heater, there they will be writing very clearly this wattage. Power is measured in watts. Okay, 1 joule per 1 second is 1 watt. Okay, so when it is expressed in wattage and voltage, this is what they two given. So V and power and wattage and voltage, this is the rating what they give. Accordingly, we will be able to calculate what is the current through the device. That is one thing. And what will be the, when it is power, current is given there, when you will be able to calculate the current, you will be able to find out what is the safe value of the current, so that you will be able to use the corresponding fuse wire over there. So these two put together, we will call it as a rating, power rating. Okay. So generally expressed in watts. We can also express it in kilowatt. Okay. 1 kilowatt is 1000 watts. Okay. So when you go for power and time, power and multiplied with time gives you the work. This is what you are getting. So V into I is nothing but power into time is the work done. This work done is nothing but the energy. If you are using electrical energy, you wanted to calculate how much amount of electrical energy is being utilized, you will be able to know two things. One is power, another is time. If I am using an electric motor of 1 horsepower, okay, 1 horsepower is 746 watt. Instead of another unit is horsepower. Instead of watt, kilowatt, I will be taking horsepower also, a colloquial unit what will be used. So 1 HP motor, if I am using for say for half an hour daily, okay, I will be using 1 HP motor. 1 HP is 1 horsepower. 1 horsepower motor I will be using for half an hour daily. If I am using that way, then I wanted to calculate how much amount of electrical energy I am using per month. Okay, so this is what you calculate using your domestic energy meters, electrical energy meters what you have installed by the board, corresponding electricity board. So they will measure the units, how many units of electrical energy have you consumed across a month. Okay, so when you wanted to use that as a unit, that unit will be called as a commercial unit, because it will be used for billing purposes. How much amount of electrical energy you have used, that for that to calculate, they'll use this unit as the commercial unit. Okay, so this commercial unit is nothing but 1 kilowatt hour. Okay, 1 kilowatt hour, if you convert it into joule, how much you will get? And 1 kilowatt hour, if it is given that way, so if I wanted to calculate how much amount of electrical energy is being across a month, so we'll be seeing that one right now. Okay.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.